about some science, like how to press buttons on that. So I will not talk much. So let's enjoy it. So what makes a good button? So neuromechanic theory and simulation.
Yeah.
So you have like 20 minutes talking.
Yeah, thanks. So as always in science, there's no solid answer to this. But as always in science, the answer is it depends, right? And I'm honored to be here. We've been studying this for a little bit over 1 year. So I don't claim that we're as far as we are in the other topics. One motivation is, well, all these fancy keyboards that are blinking up and looking at fancy that you pay hard money for. They're just gimmicks. What do you really get for that money? Of course, there are a lot of design parameters. So you can see it's something that Jacob is working on, probably many other ones. On top of that, there are so many other parameters, from the keycaps to the slant of the keypads and so on. And of course, the rest of the system, from the device to the display to the network, that's all part of the interactive button system. So how do they matter? We know that they maybe matter, right? But then how do they matter? What's the causal chain? And then, of course, well, what else matters? There are also other factors in play: human factors, practice, task-related things, individual differences. All of those come together. In a way, the button press itself is a microcosm of interaction. We're really interested in looking at it from that perspective. Now, I brought up one paper that Sanjun Kim, a postdoctorate from my lab, found this week, last week, and it's basically reporting ergonomics and performance differences between conventional keyboards and ultra-low travel keyboards. And I brought this up because this is not the kind of work we do. Okay, this is really valuable that somebody catalogs the differences. But what we want to do is something more. I think there was we actually had a really interesting lunch discussion, and much of the button research, sort of, especially from human factors and ergonomics perspective, peaked around 80s. And if you look at work, then it's sort of silent. And our task is also to speak to other groups and encourage other groups to take up on looking at buttons, because there isn't a more pervasive interface than the button. Right? It's not just keyboards, elevators, consumer electronics. It's all just about buttons. So what we try to do is we're not really interested in keyboards and keys per se, but all buttons. And this is a slowdown of somebody playing. It's actually me playing a game on a touchscreen device. And what we would like to do is to make predictions for basic aspects of input, including how we move our body, how fast and how accurate can we be in our movements when we hit spatial and temporally defined targets, and how much energy or effort and what kind of ergonomics risks are involved. Of course, this is a long-term goal. I'm not claiming that we're there yet, but this is what we try to do. Button pressing is really complicated because you have to take into account things like, you can see here, like the feedback, the anatomical differences, the sensing pipeline, the skills, task, whatever. Lots of factors, and all of them, we know that they affect performance. So I'm going to talk about, very generally first, what kind of methods we're using when we look at button pressing scientifically. We also have gone one step further and started to develop a generative model, a model that you can run. You can give a button as an input and then say that this is the user's task, and it will try to simulate the person's behavior in pressing that button. And then this is the more speculative and sort of dangerous part of my talk, and I'm willing to take your comments. Some takeaways, some things that we learned on the way during this 1 year. So let's talk first about methodology really briefly. One point that I want to make here is that we need the multidisciplinary perspective, looking at buttons not only from the physical perspective. This is a force displacement profiling device that Sanjun Kim built. It's basically trying to obtain the force displacement curve of a button. He has a collection of 50 different buttons that he measured like this, and they're basically force displacement curves that you get out. A Okay, so that's one aspect, right? And force displacement is, of course, as we actually discussed with Jacob, is one physical aspect that affects user performance and experience. For example, vibration is another one. Maybe there's the tactile sensation from the keypad, and maybe other ones. But those are physical properties you can measure, and those need to be somehow taken into account. Here's an example. We have a similar device also at KAIST, and there are some readings that they did for some button. There's the push down and the release. Something that is also important for us, we're working on simulating what is called haptic rendering. We try to you can simulate any button. In principle, what we're able to do now is to simulate a slow press with any force displacement curve. This is something that we're presenting at WIST, and if you email me, I'll send you the poster or the paper abstract, and you can look how it's done. And we found this unsatisfactory because it's not able to take a fast button press. Button press is typically from the beginning of the contact to the end of the contact is about 100 milliseconds. So this is not operating at that range. And now we have a plan to update this to also include vibration, to be faster overall. But I think this is really valuable for us because now we can, in a controlled circumstances, we can actually produce any type of a button and study systematically their effects on human performance. Which then takes us to experimental research with human subjects. So you can see a system that we use to track. There's actually a small marker on top of the fingertip, and that's used by an optical tracking system to track the 3D positioning, very high precision temporally and spatially. Then we have, this is a touch button, and underneath there's a pressure sensor, and so we get the pressure as well. So we can get almost all the physical events, well, notwithstanding vibration, for example, that are happening in this particular case. What would you ask a user to do in such a case? Would you, for example, say that, well, press the button how you like? That's an open-ended task. You can give a metronome, or you can give a rhythm, and you can ask the person to do that. You can ask the person just to activate the button. You can give temporal targets, like in a game. And that's one way of controlling how they press it. They give really different types of pressing when you give different tasks. That's an important factor in button design. You can try to incorporate button pressing to a broader setup. That could be data entry or reaction time type of a task in a game, or playing some keys and combinations. Well, one of these activities is typing, and here's an example of our studies of rollover typing behavior. So we've been looking at how much people exceeded this kind of rollover behavior, and we found that it's actually quite predictive of performance. We've been looking at typing performance from the perspective of what are the best predictors of fast performance. And one of them is rollover, the other one is a low entropy division of labor among fingers, meaning that it's always the same finger that presses the same key. And if you have high entropy, there's ambiguity in terms of whose duty it is this time to press the key. Also that people are able to look at the display rather than the keys, and so on. So these are some motor skills that you have to also take into account as a predictor of what makes a good button. This has been very popular work. We've been interviewed all over the BBC. If you're interested in what you can learn to make yourself type faster, you can Google that and find out. Finally, and this is one step further towards what I really want to talk about, we want to do simulation models. This is a MATLAB model, but we also have a robotic simulation model. And you can go and you can download the version that we had last October, at least. And the robotic model, the new one on the show, is also there, but that's an older version. Okay, so that takes us to the neuromechanics part. This is the one that I really want to talk about. And first, I just want to introduce one piece of terminology, which is the performance envelope. So you can think about somebody activating a button in an elevator or shooting an enemy in a game. There's a temporal definition of target. The button is available for some time. So the enemy is available, the target is available for some time. If you miss it, then you click too late. If you click too early, then that's also bad. And your temporal precision is defined by the width of the target that you can hit for life. Also, force is important. You don't want to use excess force. That's going to cause injuries. And if you exceed too little force, then you're going to activate the button. when we started looking at it, this is roughly 1 year ago, we were actually in a restaurant, and my colleague Byung-Chul just started tapping on the tapping on a table, and then we started discussing how is it possible that you can tap on a table. Very academic question. Okay. And then we started expanding on that, and I observed that this is actually a bit of a small miracle that we can button press. We can do a button press. And how is it possible? How is it a miracle? It's because we don't really perceive the mechanism. You are experts, and maybe you know how the mechanism works. Most people don't know how the button that they press works, right? So it's a black box. You press it. We know that everybody has tremor and other aspects of noise in their neuromuscular system. So they're not perfect systems that are exhibiting this motor action. It's also very brief, 100 milliseconds. You cannot control it like you control your hand when you grasp a ball in the air, right? So you cannot do that. And all you have are this very ephemeral sensation. How did you feel? What happened on the display? And you need to tune your responses based on that. Nevertheless, despite all these issues, we have very precise temporally and in terms of force use responses using buttons. I can use a button that I've never seen before. It's amazing. I can, if I fail in that, I actually can quickly recover just based on the first sensation. Boom, I can now press it. So how is it even possible to do that? I'm going to introduce now some elements of this theory and then show some results. How does it work? I'm going to first show a graphic Mickey Mouse version of it. Okay, so we have physical simulation of a button. It can be either the button itself, that's a perfect simulation of itself, or a virtual simulation in, let's say, MATLAB. And then we have a model of the tissue that is moved by the bone, that is moved by the muscle, that is signaled by the neural pathway, that is then controlled by the brain. And we try to identify the minimum elements of all of these to explain differences on buttons. To have a model of the brain learning to send the signals based on the sensations that it's getting back. We have a model of proprioceptive feedback, where your finger is, mechanoreceptive feedback, how you feel, and that's a mechanoreceptor model, and then a model of the eye and a model of the ear in the case of the clicky button, for example. You hear something. And now the brain must adapt its behavior based on that. So I'm not going to show the model yet, I'm just going to show how it works. So you can give a button to it, and it takes about 10 to 20 trials. So it learns to press it in a human-like manner. And again, that's because it has human-like bounds. It has similar limitations, its own sensations, and its own learning capabilities, its own muscles. And basically what we're saying is that most of the things that many of the effects that we see in button pressing are because of the physiological and physical events. We know them, and we can put them into one simulation. And when you do, then you get pretty good, at least initial results in terms of explaining differences between linear buttons, tactile buttons, touch buttons, mid-air buttons. And you get it in terms of how people move, how they use force, how precise they are in hitting enemies, and how much force they use. What's really nice about it, that there's in the middle there's this machine learning part, there's a Bayesian optimizer. It tries to find the best way to move the body, which means that it tries to find the best way to send a signal to the body, which is a muscle model. And now you can start changing the goals, for example. You can change the goal to be precise, or just to activate the button in an elevator. It doesn't matter how precise you are. Or to use as little effort as possible. For example, when I say that please use as little effort as possible, then it learns the way to push the button that doesn't go all the way to the bottom. And you can change the feedback, you can knock out a modality, you can take hearing away, or you can take proprioception away, or you can change the physical design itself of the button. Right? So you can simulate all of these aspects. So how is this neuromechanics modeling working? So there's basically nothing magical there. It's common sense that there's a brain. The brain sends some signals, but it cannot directly control the physical. It's enveloped by the physiological. So when it goes this way, we have the spine, that's corrupted by noise, sending the signal to the muscle. Muscles are corrupted also by noise. And then that's then controlling the physical thing, which is the bone and the tissue touching or interacting with the button. And then the other way around, we have our senses, mechanoreceptive, proprioceptive, other senses that we know really well. We can also model the way they do that. These processes are called transduction. There's transduction of energy from each side, right? But in a particular way. I'm going to take one more level deeper. So there's the brain that sends a signal through the spine that is transduced to action potential to our muscles that are moving our limbs, that are interacting with the physical device, that are then causing stimulation to our sensory organs, physical stimulation, that then our sensory nervous system is then integrating and interpreting in some way, and then the brain adapts itself. I'm going to save you from some of the theoretical parts, unless you really insist that you want to see that. But it took us quite a long time to get there. I'm going to show some parts of it, but just to give you an idea of what was really the key part to get this working, because we struggled a lot, was the idea that when people try to hit a button precisely, what they do is they try to minimize prediction error. So their brain tries to make a prediction of what kind of sensation it gets back. Okay, and if it gets exactly that kind of sensation, then it's controlling the button, right? It can never really control the button, right? Because it's a physical thing that doesn't have access to it. And then what it's also doing is has a probabilistic model to try better and better guesses on how to control that. Obviously, if you try random movements, then it's going to be successful. It's a robot doing random movements, just to show you that this is not a trivial problem, right? You cannot trivially solve it. Okay, so I'm going between the virtual and the physical, but in both the robot and the virtual MATLAB model, there's basically basic bounds of biomechanics of the human muscular system. You have a bone model, a tissue model, you have a button model, well, in this case this is a spring damper mass model, but it's not the only model, but it's a minimal model that you need to do. Basically, now what you can do is you can simulate all of this physically. There's muscle pulling, muscle pushing, and then that's acting on the bone that is pushing down, and there's a physical event, and then you have all of that is driven by a signal that the brain sends. Okay? And the brain sends it to the muscles. Muscles are acting on the bone is pulling the whole finger down, and interaction happens, and then some sensory stimulation happens. And of course there are senses as well. We implemented hearing model, the vision model, proprioceptive model, mechanoreceptive model by reference to literature. These are really simple models, but just getting the gist of it. How it's done in a robotic implementation, you have of course a real button. You don't have a physical model of the button. It's a real muscle, real button. You have a heel type muscle model. It's a well-known muscle model implemented very easily in software. You have a silicone fingertip to model the tissue. Underneath there's a pressure sensor for tactile sensing that we then in software manipulate in a way that then corresponds to mechanoreceptive sense. And then in the heel type muscle model, actually in the joint, there's a joint angle sensor. And all of them are corrupted by noise. And if you don't have noise, this is an actually essential aspect of all these models. If you don't have any noise, then you have superhuman robotic button presses. We don't want that. We want human-like button presses. How much there is time now, Sayan?
Yeah, I think 5 minutes.
5 minutes. Talking or with question? Talking. Okay. So let me quickly show some key ideas. So one of them is cue integration. So when I press a button, many things happen. Actually, all the senses are on all the time, right? For example, tactile sensation, hearing, seeing something happening on the display, and you can model them as means and variances over time if you're interested in how precisely people press buttons. Now the question is, how do you integrate that? You could use a Bayesian approach, or you can use what we did, maximum likelihood estimate. What it basically does, it makes the assumption that people know how reliable different senses are on average, right? And they use this knowledge to correct for whatever signal they got back. So weighing their importance based on that. So basically then you can, from this multitude of signals, you get one interpretation. And this is when the button was, it's actually not when the button was activated, but when I feel that the button was activated, right? It's an integrated percept over time. Now what's nice, because you integrate optimally all the information from the cues, you can then kick out some cues. So here's a robot that doesn't have any tactile sense. It's really hard to activate the button. You can imagine yourself anesthetizing your finger and trying to press a button. It would be very hard. So it shows the importance of this sensory modality for button pressing. The other thing that we started modeling is the objective function of the user, and we did it in a way that you can express the differential contributions of how precise they want to be over time, whether they want to activate the button or not, whether they want to contact the button or not. And typically these are high because they always want to, when you press a button, you want to. And then of course the muscle force, whether you want to emphasize an ergonomic button press or not. So this allows to model different tasks that we might give to the user. Here, for example, this is a robot that just doesn't have any muscle effort terms. It's pressing the button to get the maximal signal so that it can more precisely time its motor commands. It's trying to hit the floor. It doesn't matter if it could break the finger. How the Bayesian brain operates here is that it tries to make a prediction about what kind of sensation will I get if I press the button like this. It starts with no clue about the world. It's just, and then it makes one guess. Let's say I'm pushing here. Then it gets a sensation that, okay, this is the integrated perception that I got. And then it tries to improve over time and it develops an internal model. So that allows it to recover, to make predictions and all that. And it's a very efficient way of learning. 10 to 20 trials and you get a really nice performance. Okay, so does it work? We compared a lot against existing literature on how precisely people can push buttons and touch buttons and mid-air buttons. That we know from literature, push buttons are better than touch buttons, that are better than mid-air buttons, that are the worst in terms of success rate as well. The simulation replicated this order, right? It doesn't make sense to compare the absolute numbers that they had. The order was replicated well by this model. It made the prediction that tactile button is better than the linear one. Uses a little bit less force. It gave this kind of kinematics prediction for mid-air buttons, and this is from previous work. This is human, and this is the model. So it's a nice, elegant curve. You can look for the paper for results, but they are sort of in the ballpark of good results. When we ask the model to do a light touch, then the force is similar to what has been reported in the literature. Yeah, I think I'm going to skip that part, just talk about limitations. We don't have really good muscle or joint models. We don't have a noise model called signal-dependent noise. We have just absolute noise. We don't have any force perception. This would be interesting. We don't know how to exactly identify those parameters. Now, finally, to my original question of what makes a good button, here are some things that we, with Sanjung, decided that are worth mentioning here. This is one tactile bump. This is from the paper. Sanjung had identified these features and given names. What he's saying, what the results are implying, is that you, from the tactile versus the linear button, from tactile you get two signals to the brain, two sensation signals, two peak signals that are distinguishable. But because of the bump itself, the latter signal is dampened a little bit, right? Because it takes some of the physical energy away. If you have low travel and shallow activation, then it's going to be really good for fast response. But and what's also good for the tactile bump is called cognitive landmark. So when you type and you look at the display, you know which finger has pressed which key. So you have this sensation, oh, I slipped the key, and then you do something else. But overall, the differences that we find are pretty small. So in the order of below 10%. But they can be significant, and this was another paper that was quite widely popularized. You can improve that with an analog keyboard and a software side activation point called impact activation. Impact activation, so this is a regular way of activating the button, doing the downstroke. And what we do is called impact activation that looks at the maximum, the peak energy transfer and it takes that as the point of activation. And you can do this in software side, and people improve their performance, temporal precision a lot, right? It doesn't mean reaction time. Reaction time is different. Temporal precision improves a lot, 94%. And there's less variance, meaning they're more reliable in their responses. Voting liked this result a lot. Tweeted that they're glad that their keyboard can now be put into use. Something researchy like this. The third takeaway concerns latency. You often think about the discussion that I see about latency is just about the mean of latency. Latency is always a distribution, right? And according to this model, what matters more is the variance of that distribution, especially for small ranges of latency, because it's important for the human brain to be for the event to be predictable, so it can tune its response. It doesn't matter if it's 5 or 15 milliseconds or 50 milliseconds, but it does matter a lot, for example, if there's a source of latency coming from the network that is variable. It makes it impossible for the brain to correct that. Finally, going back to the original video that I had, and this discussion about why is the touch button worse, and there's of course a lot of discussion about that when the iPhone came out. What are we losing with the touch screen versus the physical keys? And of course the first reaction was that, well, you lose tactile feedback, but actually that's not true, because when you hit the surface you get tactile feedback, right? So unfortunately that's not true. So what the model was predicting is that then when you do repeated key pressing, like in a game on a touch screen, the starting point, the starting height of your finger is more varied, right? And that's actually making a big difference. If you fixate that, you get much better performance with touch screen as well. And the other one is, of course, the sensing pipeline is quite intrinsically more varied. You have more latency, as I discussed, which is detrimental to performance. So to summarize, I started with this Mickey Mouse description here, and you have the problem is that the brain has to control the hand that is controlling the finger that is interacting physically with the button, and then somehow it must make sense of the sensory feedback that is getting back. So you need neuroscience, physiology, and physics to understand button pressing, which has been somewhat revelating to us. So button pressing is way more complex than people have thought. Fortunately, we can do simulations like this thanks to machine learning, thanks to our understanding of electrophysiology and the way we can simulate those using EE, signal processing, and thanks to very sophisticated tools that you have, for example, in MATLAB doing biomechanical simulations. That's it. Thank you.
You guys make questions?
I have questions.
Yes, please.
So my first question would be, did you consider using sound as another feedback mechanism for your input?
To us, it's treated similarly as the other cues. What matters is how distant it is from the other cues in time and how varied it is. And the second aspect that is important is the physical strength of that signal. Right? If you have very inaudible signal, it's not going to be contributing to your cue integration. So to the extent that this model is applied, then we didn't really need to look at that. But I can guess that if I look at the regular clicky buttons, they would contribute to the cue integration by adding yet more reliable signal that you can use. But if you think about audition that comes from the after the network and the system processing from the computer system itself, that can actually be detrimental.
Yes.
So that can be discomfort.
Next question, comment. So the impact sensing is exactly the same as how a piano works, because the piano works on acceleration. It does not work on velocity. How you impact.
Yes.
How you get your sound.
Now you made me embarrassed. I hope that this is mentioned in the paper. Thanks.
Yes.
Any other question?
If you're interested in this, email me. I can send any of the stuff. If you come to Helsinki and want to see some of the stuff in action, please visit. Okay. This guy, I guess they could nominate. So it was a presentation at KAI, one of the leading conferences, and I had 300 people in the room, very popular. And then I heard that most of the people didn't get it.
It's only 15 minutes.
But the old gurus did get it, and they liked the words.
Anyways, thanks. Any questions? Thank you very much for your long 2 minutes. I will not, because it's a little bit break now.